All right, thank you. So today we're going to be talking about sort of Baire degree perspective on the difficulty of finding isomorphisms. Right, so this is joint work with Selwyn and Coherton. I'll start with sort of the general question. So given two copies A and B of some structure, countable structure here is we can ask the question of how hard how is it to find an isomorphism All right, so this is a general question that in computable model theory often asked, right? And so this is related to like the degree of categoricity, right? So if we assume that A and B are computable, we can sort of ask, what is the least degree, right? One sort of way of trying to answer this, more general hardness here is a bit vague, is to sort of say, okay, what's the least degree that could compute an isomorphism? Right. So one notion. Right. So that's least D, such that if A and B are computable, then there's a decomputable isomorphism. This leads to notions like computable categoricity. So we could say M, the general structure, right, is computably categorical. If 0 is the degree of categoricity. Right, so an example of this would be, if we look at the rationals with the standard ordering, right, as a linear order, this is computably categorical. CC. This gives us an example here. Right, and these have been studied sort of quite a bit. Like a general result is that it isn't always true that there is a least degree that can compute an isomorphism between any two structures. 2 copies of M, right? And so, yeah, so in this talk, we're going to be looking at a different perspective, right? A different way, a common way of measuring, the difficulty of problems that comes from sort of first map ideas of sort of Weihrauch degrees. So we'll give all right, so in this case, we're sort of interested in problems. So this is going to be some, partial multifunction on Baire space. Essentially sort of defined by a subset of Baire space across Baire space, but sort of we view it more as a function with sort of, we call instances or inputs that come from here, and then there may be multiple solutions, but not everything needs to be a valid input. And so we can view lots of different stuff with problems, and so we're also interested in sort of reduction notions. So if we've got Q and P, definition, we say that Q is reducible to P if there are computable functionals I and psi such that we've got if Q is an instance of Q, then we've got our forward functional phi of Q should be an instance of P in the domain. And then we need sort of translations of solutions. So if S is in the equal to P of this phi Q, so the multifunction, so there could be multiple S solutions to phi of Q. Then next step is we want to be able to translate the solution P to a solution to Q. And so we would say phi of both the original input and this new solution equal to, or as a solution to the original problem. All right. That's a definition of Weihrauch reducibility. Yeah. And you can see it's a measures of difficulty of problems, right? So the idea is, okay, I can use P to solve Q. I've got a computable way of turning problems in Q to problems in P. So if I had some magic way of getting solutions to P problems, I could then use it to get solutions to Q problems. All right. We'll do some examples next, maybe. So we've sort of got ID, right? This is sort of the problem. It's a standard, identity function on Baire space, right? This sort of sits the Weihrauch degrees, one of the sort of main simple problems. Yeah. Then we've got And some other problems that we might be interested in or discussing here would be like the end. So this is a choice on the natural numbers, and so instance, just, anything, so just some sequence, and a solution going to be some n that is not in the range of the P here. Right, and so the idea is we've got to choose something that avoids everything listed here. And that's just a strictly harder problem. All right. Some other examples might be like lim. So lim instance is going to be a sequence, all right, of elements of Baire space, and a solution is going to be the limit of the sequence. So this is sort of implying the sequence has to actually converge to be an instance of lim. So we're using the partial domain. And this sort of measures, more difficult sort of problems, similar to like computing the Turing jump, or equivalent. That's more difficult. And I think so the main one, was the final problem for the talk, is a choice on the Baire space. So choice on natural numbers, choice on the Baire space, sort of much harder problem. Different ways of phrasing that, but the way that's more useful for us in this talk is going to be instances. There's going to be some tree in the Baire space, and a solution is a path, infinite path on C. That's some example problems of Weihrauch degrees. Now, also looking at the problem of isomorphisms as Weihrauch degrees. Over here. So we're going to define new problem for a fixed structure M. All right, we can define categoricity problem on M as problem with instances A All right, so viewing the instances as a pair of structures, copies of M, and we sort of can say on domain omega, so on the natural numbers are sort of our base elements, and then we've got a way of interpreting the relations. So this, unlike in our previous categoricity case, right, here we're letting these be arbitrary elements of Baire space. So, A and B, there's no computability restrictions other than that we can, we get given the standard copy of the domain being omega. right? But they can be presented in very non-computable ways. Yeah, right. And the solution is solution, as we should expect, is an isomorphism from A to B. So this was originally this definition here. It was originally sort of suggested by Baire. All right, and so this sort of, the different sort of idea. So given this definition, right, we could ask sort of, okay, we fix some particular structures M or classes of structures, we could see what happens to the Weihrauch degree of this problem. And so maybe one you could see here is that IG is Weihrauch equivalent to hat of M if M is uniformly computably categorical. So this sort of means if I can uniformly compute an isomorphism from any two copies, right? This is a uniform way, right? Then I can, ID is enough to compute this problem, and assuming at least M has computable instances, it's going to be above ID. This is a base example, but we do have sort of more complicated things like if M is relatively, so it works with relativization, then we have that. So this is the first result, one of the big results that one of the first results I got with Turn and Selwyn is that M is relatively computably categorical. Then we have that cat of M is below the end jump. So this is a sort of harder version of choice on the natural numbers. And in fact, this is a sharp bound in that we've came up with a computable structure M whose problem finding isomorphisms CAD in is exactly the end jump. So some other variations of the problem we got. Some other sort of example problems here is we've got theorem that omega, the standard ordering, right? We take if we look at the degree of this problem, that needs to be exactly the degree of lim. So this sort of matches up nicely with our intuition about degrees of categoricity. So if you've got a copy of the linear order omega, once you know the successor relation, like which comes next, that's enough to compute any isomorphism, the lim corresponding to computing a jump. So it says, okay, I give you this input linear order, I can find its jump, I can find an isomorphism, and it's turned out to be sharp, and that's enough. But uniformity is important here, and we've got this interesting result that we look at omega and then we add a second copy, all right? So it's the same degree of categoricity, but in fact equivalent to this slightly harder problem, which is choice on the natural numbers star lim. So this here is the sort of compositional product. So sort of a technical definition, but sort of intuitive understanding is I first do this problem on the right, and then I look at my solution and I possibly computably change that to give an input to this problem, and then I do this problem. And so the idea here is once you've got the successor relation, right, you can compute an isomorphism, but you still need to know the starting points. And one jump is enough to tell you the first starting point, but it's not enough to tell you the starting point of the next part. And for that, you sort of have to make a bunch of guesses, and eventually you'll sort of, you know, the successor is something with no, which is not the successor of anything. So eventually you can make a right guess, and that's sort of what the CN is encoding here. Yeah. There's also maybe another sort of interesting non-result, or not sort of negative result, is that there is no structure M such that we look at WK. So this is Weeks-Koenig's lemma. So this problem, basically given a tree on Cantor space as an input, find an infinite path. Right. This is no problem that lies between this problem and other problem at LPO, and that sort of won't get the idea, but it's also a weak problem that's sort of strictly above ID, but not, you know, it's still one of the lower down problems in the hierarchy. So this gives examples saying, okay, we can't achieve every degree or every Weihrauch degree as an instance of this problem. You know, so the fact that we're looking at a categoricity question, you know, does impose some restrictions on, you know, what the problem might look like. Okay, so the next quick thing I'll look at is this a general problem. So define just the general cat problem. We view this as just the union overall models of the smaller problems. Right. And so this problem is a general problem. And so its instance is here A and B, which are isomorphic. Right? But there's no restriction on what model A and B come from. Right? And so in that sense, you can sort of view it as a union of all these other instances. You might be asking, you know, what is the degree? Sort of, as you know, you might have got an idea from Johanna's talk before mine, right? Like this is related to sort of, you know, for isomorphism in some sense, and sort of it's vaguely asking how hard is it to find an isomorphism, right? And you expect something along the lines of sort of, you know, Klinizo to sort of come up or something high like that to be required, right? And perhaps one of the sort of natural ways of viewing this sort of problem is going to show that look at this general cat problem, in fact below choice on the Baire space, right? Which in the Weihrauch degrees kind of looks like, you know, related to problems like, you know, finding infinite descending sequences and ill-founded linear orders and so forth. So the sort of idea for how this theorem works, right? We said take a pair of structures, isomorphic, right? And then we want to compute the tree of partial isomorphisms. So this is sort of going to be given by, you know, view sort of a tree of partial isomorphisms. We want to view as something like a sort of series of pairs, right? We map, so we sort of want, you know, sigma is on this tree. If you know, all initial segments are on the tree, and we want to have things like is sigma to be a finite partial function from the V, and we want that the atomic diagram of the domain of sigma, you know, is the same as range of sigma. And then we also need, you know, to ensure we get an isomorphism in this tree, we need to ensure things like, you know, n is less than the length, 2 times the length of sigma. 2n is less than the length of sigma. We want that, you know, n is in the domain and range. So continuing the proof here, we've got this tree of isomorphisms, then we can argue that on this tree is our isomorphism. Right, and so we've structured in such a way, okay, the atomic diagrams agree, and all the relations agree. We get an infinite path. It has to include every n in its domain and every n in its range, so it's got mapping all of A onto all of B. And so we end up that completes the reduction. Important, right? Because once we know A, we know the atomic diagram. This tree is computable from A and B. So we've got a forward functional is just given A and B, produce a tree. The backward functional is, we basically got the isomorphism already. It turns out we've also got the other direction as well. First in the Baire space is in fact reducible to the general cat problem. So this proof involves using this concept of a universal tree, maybe universal in quotes because they're vague. So U we can define U in terms of its sort of structure type. The following properties and we're thinking of U as a structure in the language of directed graphs. Right, this is similar to what Dan was talking about earlier. We've got some root, and then we can think of, if we want to think of it as a structure, we're considering nodes related to the root. This is sort of important when we consider isomorphism of U. We're allowed to sort of, there's no ordering on the children of the root. We just care about the structure. All right, so the properties we want you to have are the following. So we want U has an infinite computable path. Right. And we want that for all alpha less than omega 1 ck, okay, and Actually, we'll write it for all nodes X and U and alpha less than omega 1 CK and the rank of our node X. So the rank can be defined sort of, as you usually would for trees with sort of transfinite recursion, where the rank of leaves is just 0 and the rank of a node is just a primum of 1 plus the rank of each of its children. And so ranks have to strictly go up as you get closer to the root. Right? If something has an infinite path above it, then its rank is going to be infinity. So for all alpha below omega 1 CK and the rank of X, right, we have that there is a child Y of X such that the rank of, there's actually infinitely many yes. Less than both of these, yeah. And then the other condition right here is we need that for all nodes X of rank infinity, so these are all the nodes that have an infinite path above them, there are infinitely many children Y of X such that rank of Y is equal to infinity. That sort of completes the characteristics of U. And so if we've got a lemma such a U exists, I won't go into the details, but it is possible to construct a U with these properties. The way we're sort of thinking of it is every, if you look at it on U, every node has a rank, and then sort of above it, it's got, all its children have all the possible ranks they could have, right? A witness there. So, every finite or, well-founded rank is possible, but also if it happens to have infinite rank, then every infinite rank occurs infinitely often. So it's sort of a very homogeneous structure. And perhaps another sort of useful property is that if T is computable, then T cross U, right, so this is going to be the set of all pairs sigma tau and the sets T and U, right, such that same length or the same distance from the root. And then extensions are just pairwise extensions here, right? So this tree here happens to be isomorphic to just the U, just the standard U we've been dealing with, right? And so the idea we need another condition, and has an infinite path. Okay, so this is the property we really want you to have, is that this property here. So we sort of take some arbitrary tree, it's got an infinite path, it's computable, it looks kind of weird maybe, and then we sort of want to homogeneize it. Well, if we take its product with U, then along the infinite path, we kind of get a copy of U, and this homogeneous property that we sort of got every possible rank is sort of witnessed above things in U means that, okay, it's going to end up being isomorphic to U. So then the final part of the proof, right, is we've got take we need to this relativizes. So the idea is, okay, given some arbitrary tree T now, I can look at some arbitrary tree T with an infinite path, so an instance of choice, right? We take it, product with the universal tree but built relative to T, and this sort of allows us to deal with the fact that arbitrary trees may have things of rank above omega 1 ck, right? But if they do, then that tree sort of is enough to compute ordinals above omega 1 ck, and so the universal tree relative to it is going to be larger and going to have things of higher rank occurring in it. And then this is going to be isomorphic to the universal tree, U relative to T, and we can, put, these two inputs into our isomorphism problem cat, right? And when it produces an isomorphism, on the right-hand side, we've got a computable infinite path that remains even when we relativize this computable path, and then we can say, okay, well, the computable path on one side gives us a computable path on the other side with the isomorphism, right? And a computable path in T cross U looks like a path in U and a path in T. We don't really care about the path in U, but the path in T is the solution we want to choice in the Baire space. All right, so that concludes main proof. Like 15 minutes, right? Or a little bit more? I've run out. Okay. I think I'll finish there. For every tree with an infinite path, yeah. I'm assuming. So yeah, so the point, so this proof, I sort of gave a sketch of like what happens when it's computable, and when it's not computable, we kind of relativize. So this construction of U, I can relativize it to an input, and so when I can relativize it to that tree that's not necessarily computable, and then like this general property, in order for this to work, I need T to have an infinite path, but I also need the well-founded parts of T to have rank below omega 1 ck, right? An arbitrary tree may not have that, but once I relativize and I then construct U, guarantee that this new u relative to t, does have that property that they're all, omega 1 relative to whatever t is. Jump, yeah. So that was, so it's choice on n, jump. Yeah. All right, so that one, so there's a little bit, so it's between WKL and LLPO. So there are actually, there's no M. There is actually M that is between WKL and ID. It has to be strictly between because otherwise it will break this theorem. But yeah, and so it's so it's like one of those ones which is like, I think you've got a sequence of zeros and ones, and the answer is like 1 if there is 1, or 1 occurs somewhere and 0 otherwise. Is that right?
Sequences, element, the only one that you can go out, doesn't go out.
Mm-hmm.